Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1925 marks a profound schism in the history of physical thought, a moment when the very grammar of reality was written. At the epicenter of this rupture stands a work of startling genius and youthful audacity, Werner Heisenberg's paper, Über die quantentheoretische Umdeutung kinematischer und mechanischer Beziehungen, or on the quantum theoretical reinterpretation of kinematic and mechanical relations. This essay explores the intellectual genesis, the intricate technical heart, and the expansive legacy of this singular document, which effectively terminated the old quantum theory and inaugurated the age of quantum mechanics. It was a pillar of the new physics, constructed from abstract principles and a rejection of comparable, visualizable models, a testament to a mind willing to follow mathematics into territories where physical intuition feared to tread. To appreciate the paper's revolutionary character, one must first survey the landscape it transformed. The early 1920s found physics in a state of controlled crisis. The Boas-Sommerfeld model of the atom, a brilliant hybrid of classical mechanics and ad hoc quantum conditions, had achieved remarkable successes. It explained the spectral lines of hydrogen with stunning accuracy, yet this success was circumscribed. The model failed spectacularly when applied to the helium atom, and it struggled to account for the anomalous Zeeman effect. Its foundations were philosophically precarious, grafting quantum jumps onto classical electron orbits that were, by their very nature, unobservable. Niels Bohr himself was acutely aware of this inadequacy, promoting his correspondence principle as a heuristic guide to bridge the gap between the familiar classical world and the strange quantum one. The principle suggested that for large quantum numbers, the predictions of quantum theory should merge with those of classical physics. It was a powerful tool for insight, yet it remained a guide, a set of constraints rather than a coherent dynamical theory in its own right. The intellectual stage was set for a fundamental reconstruction. The direct impetus for Heisenberg's new approach emerged from a study of dispersion, the scattering of light by atoms, the work of Rudolf Ladenburg, and subsequently the more advanced formulation by Hendrik Kramers, in collaboration with Heisenberg himself, proved to be the crucial technical precursor. The Kramers-Heisenberg dispersion formula, developed in 1924, successfully describes scattering by relating it to the probabilities of quantum jumps between stationary states, represented by Einstein's and B coefficients. The formula's success was rooted in its reliance on quantities associated with transition frequencies and amplitudes, while completely avoiding any mention of the electron's orbital frequency or radius within those states. It operated with the building blocks of observation, the spectral lines, and their intensities. This experience primed Heisenberg to consider that a complete theory might be built exclusively from such observable quantities. In the summer of 1925, while recovering from a severe bout of hay fever on the isolated island of Heligoland, Heisenberg took the decisive conceptual leap. His central, guiding axiom was a form of radical empiricism. A physical theory should be built using only quantities that are, in principle, observable. This immediately rendered the classical concepts of electron position and momentum as continuous functions of time, xt and pt, illegitimate. One could observe the frequencies and intensities of light emitted during an atomic transition, but never the electron's path during that transition. Heisenberg sought to replace the classical kinematic variables with new mathematical objects that were constructed directly from these observables. He began by considering a classical Fourier series representation of a periodic motion, where a quantity-like position is expressed as a sum of oscillating terms. For an atomic system, he proposed a profound reinterpretation. Instead of a single fundamental frequency and its harmonics, an atom possesses a whole collection of transition frequencies, omega m, corresponding to jumps between an initial state n and a final state m. Consequently, the classical position xt had to be replaced by a two-dimensional array of complex numbers, which we can denote as x sub n m, representing the amplitude for the transition from n to m. The time-dependent part of these terms would oscillate at the observable transition frequencies. The true challenge, and the paper's technical core, lay in defining a rule for multiplying these new arrays. If position x is an array of amplitudes, what is the array corresponding to position squared, x squared? A naive, element-wise multiplication failed to satisfy physical requirements. Heisenberg, guided by the correspondence principle and the structure of the Kramers dispersion formula, formulated a new multiplication rule. To find the m component of a product of two quantities, say and b, one must compute the sum over all possible intermediate states k of the product of the k component of A and the m component of b. This rule, A b sub n equals the sum over k of a sub nk times b sub km, was invented on the spot to ensure that frequencies combined correctly, following the empirically established Ritz combination principle, which states that the frequency of a transition from state n to m is the sum or difference of frequencies of transitions passing through an intermediate state k. When Heisenberg applied this new multiplication scheme to the fundamental variables of position, q, and momentum, p, he stumbled upon a startling result. The product of position and momentum depended on the order of multiplication. The quantity p times q was demonstrably different from the quantity q times q. This property, non-commutativity, was entirely alien to the numbers of classical physics. He went further and derived the specific form of this difference, using an old quantum condition from the Bohr-Sommerfeld theory, the Thomas-Kuhn sum rule. He was able to show that the expression p times q minus q times p for all diagonal elements was a constant, the imaginary unit I multiplied by Planck's constant divided by the quantity 2 pi. This was the first statement of the canonical commutation relation, the bedrock of quantum mechanics. He had built a new kinematics from scratch, and it yielded a dynamic condition that inherently contained the quantum of action. As a first test of this new mechanics, Heisenberg applied it to simple physical systems within the paper itself. He successfully calculated the energy levels of the one-dimensional harmonic oscillator and, more significantly, showed that the formalism could handle the anharmonic oscillator, a problem that had been intractable in the old theory. He demonstrated that his method naturally produced discrete, quantized energy levels, fulfilling the most basic requirement of any quantum theory. The paper was finished in July 1925 and sent to his mentor, Max Born, in Göttingen. The reception of Heisenberg's manuscript is a story of insight and collaboration that rapidly accelerated the revolution. Born, a formidable mathematical physicist, studied the curious multiplication rule and, after a week of intense thought, had a moment of profound recognition. He identified Heisenberg's ad hoc rule as the standard definition of matrix multiplication, a subject he dimly recalled from his student days under Jakob Rossens. This insight was transformative. Heisenberg's abstract arrays were matrices, and his new mechanics was matrix mechanics. Born, with the crucial assistance of his brilliant young student Pascual Jordan, immediately set to work reformulating and extending Heisenberg's ideas into a rigorous mathematical framework. Their paper, Zur Quantenmechanik, submitted just 2 months later, placed matrix mechanics on a firm footing, identifying position and momentum as infinity-dimensional matrices and deriving the canonical commutation relation pq minus qp equals h bar over I times the identity matrix in its general, off-diagonal form. The final piece of initial validation came from the famously critical Wolfgang Pauli. Initially, Pauli expressed deep skepticism towards Heisenberg's Göttingen learnedness, finding the abstract algebra distasteful. However, he was persuaded to apply the new methods to the one problem that would serve as the ultimate arbiter, the hydrogen atom. Using matrix mechanics, Pauli succeeded in deriving the complete Balmer series for hydrogen, as well as the effects of a crossed electric and magnetic field. It was a triumph of calculation that the old quantum theory could never achieve, and it converted Pauli into one of the new mechanics' most ardent and formidable proponents. His success, communicated in a letter to Heisenberg, cemented the theory's status among the physics elite. The collaborative momentum continued with the Drehmoner Arbeit, the three-man paper by Born, Heisenberg, and Joule, published late in 1925. This comprehensive work presented the fully developed theory of matrix mechanics, establishing its mathematical apparatus for treating systems with many degrees of freedom and laying the groundwork for a quantum field theory. The story of Heisenberg's paper would be incomplete without acknowledging the parallel development that emerged shortly thereafter. In early 1926, Erwin Schrödinger, working from a completely different philosophical starting point inspired by Louis de Broglie's wave-particle hypothesis, published his papers on wave mechanics. Schrödinger's theory, formulated with the familiar mathematics of partial differential equations, offered a more continuous and visualizable picture, featuring a wave function evolving in spacetime. He was openly critical of matrix mechanics, which he termed frightful and lacking in Anschaulichkeit, or intuitive picturability. The existence of two seemingly disparate yet successful quantum theories created a brief period of confusion and intense debate. The resolution came with extraordinary speed. Schrödinger himself, in a 1926 paper, proved the formal mathematical equivalence of his wave mechanics and Heisenberg's matrix mechanics. They were two different representations of the same underlying abstract structure. This revelation underscored the profound nature of what Heisenberg had initiated. He had uncovered a deep syntax of nature, one that admitted multiple mathematical dialects. The ultimate synthesis and generalization, however, came from a third, uniquely insightful figure, Paul Dirac. Viewing the developments from Cambridge, Derek was less concerned with the specific formalism of either matrices or waves. He perceived the abstract algebraic structure common to both. He recognized that the crucial discovery was non-commutativity. In a masterstroke of insight, Derek showed that the quantum mechanical commutator, the expression a b minus ba, was the quantum analogue of the Poisson bracket of classical mechanics. This discovery, central to his transformation theory, elevated quantum mechanics to a new level of elegance and power. It provided a universal prescription for quantizing any classical theory and unified the matrix and wave approaches within a single, more general framework using abstract operators and state vectors. Derek's work grew directly from the seed planted by Heisenberg, demonstrating how a single, radical reinterpretation of kinematics could blossom into a complete and abstract theory of dynamics. The influence of the 1925 paper was thus immediate, profound, and cascading. It directly spawned the work of Born and Jordan, provided the tool for Pauli's crucial calculation, and established one of the two pillars that Schrödinger would soon show to be part of the same edifice. It provided the core, non-commutative algebra that Derek would generalize into the language of modern quantum theory. In retrospect, the 1925 paper on my interpretation possesses a certain intellectual irony. Heisenberg set out to create a physics grounded in observation, yet he produced a highly abstract, non-visualizable mathematical formalism. His rejection of hidden classical mechanics led to the discovery of a hidden mathematical structure governing the quantum world. The paper's enduring legacy is this very structure. It established that physical observables are represented by non-commuting operators and that the state of a system is a vector in an abstract space upon which these operators act. It decisively broke with the classical ideal of a deterministic, picturable universe, replacing it with a framework built on probability, amplitudes, and intrinsic indeterminacy. Heisenberg's work was more than a new theory, it was a new epistemology for physics. It taught that the goal of science was to codify the relationships between measurements, a more modest and yet more powerful aim than describing a noumenal world behind the phenomena. The young physicist on Heligoland, by focusing with unparalleled discipline on the observable, inadvertently became the architect of an abstract reality, one whose strange and beautiful rules continue to govern our understanding of the cosmos. His reinterpretation was, in fact, a creation, giving physics the very language it needed to speak about the quantum realm.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.